This week, we're going to talk about probability. The concept of probability is not foreign to health professions. People use the term probability many times each day. For example, physician says that a patient has 50-50 chance of surviving a certain operation. Another physician may say that she is 95% certain that a patient has a certain disease. Upon completion of this lecture, you will be able to first define probability, and then be able to compute and interpret unconditional and conditional probability, and also be able to describe the property of probability and probability rules, and also be able to evaluate and interpret the independence of events. And lastly, be able to apply Bayes' theorem when calculating screening test results. The probability of an event tells us how likely it is that an event will occur. The probability that an event will occur is between 0 and 1. The probability of 0 implies the event will never happen, and probability of 1 implies the event is certain to happen. Usually, events with probability of 0 and 1 are not very interested to discuss. The notation P with something in parentheses after, such as P of A, is used to represent the probability of A happening. We can include more descriptive notation such as P of male or P of having diabetes if we wish. Or we can use letter to represent our event in the interest as a shorthand notation. The two views of probabilities. The subjective view of probability is an estimate that reflects a person's opinion or best guess about whether the outcome will occur. It is important in medicine and public health fields. It helps form the basis of a health profession's opinion based on information gained in the history and physical examination about whether a patient has a specific disease. Such estimate can be changed with the result of diagnostic procedures. Objective view sees probability as an objective phenomenon derived from objective process. It is known that the probability of flipping a fair coin and getting a tail is 0.5. If a coin is flipped 10 times, is there a guarantee that exact 5 tails will be observed? If the coin is flipped 100 times, with thousands flips, as the number of flips become larger, the proportion of coin flips that result in tails approaches 0.5. In classic probability, we assume that an experiment can be repeated many times and that there is one or more outcomes that can result from each repetition. Then the probability of a given outcome is the number of times that outcome occurs divided by the total number of repetitions. I'm going to use this example to demonstrate how to compute marginal and conditional probabilities. Let's say there is a hypothetical population of 100 people. The number of individuals are placed in this table according to their genders and blood type. Marginal probability are named so because they appear on the marginal of a probability table. It is probability of single outcome. In the example of previous slide, the probability of male and the probability of blood group A are marginal probabilities. The probability of male is calculated as the number of male divided by the total number of subjects. So you have 50 divided by 100 is equal to 0.5. A conditional probability is a probability of an event on a conditional that certain criteria are satisfied. Think about this question. If a subject is selected randomly and found to be female, what is the probability that she has a blood type O? Now the total possible outcomes constitute a subset of the total number of subjects, and this subset includes all females. Then the probability of O given F is calculated as 20 divided by 50, which is equal to 0.4. Joint probability refers to the probability of occurrence of two or more events. For example, the probability of being male and belonging to blood group AB. There is an intersection of two events. Being male and having AB as his blood type. Then the probability is calculated as 5 divided by 100, which is equal to 0.05. Here are the properties of probability. The probability of an event, which inform us of the likelihood of its occurring, can range anywhere from 0 to 1. If an outcome cannot occur, its probability is 0. If an outcome is sure, its probability of 1. One practical use of this rule is that it can be used to identify any probability calculation that come out to be more than 1 as incorrect. If two events are mutually exclusive to each other, then the sum of probability of mutually exclusive outcomes are equal to 1. For example, there are 4 possible blood types, A, B, AB, and O, and they are mutually exclusive to each other. Then the probability of having A blood type plus the probability of having B blood type plus the probability of having AB blood type plus the probability of having O blood type is equal to 1. In the probability and in its application, we're frequently interested in finding out the probability that a certain event will not occur. An important point to understand here is that event A does not occur is a separate event that consists of all possible outcomes that are not in A, and is called the complement event of A. We will write not A, or A bar, or AC to denote the event that A does not occur. Property number 3 deals with the relationship between the probability of an event and the probability of its complement event. Given that event A and event not A together makes up all possible outcomes, and since rule number 2 tells us the sum of the probability of all possible outcomes is 1, the following rule should be quite intuitive. The probability that an event does not occur is 1 minus the probability that it does occur. We will go over some probability rules. Two events that cannot occur at the same time are called disjoint event or mutually exclusive event. The occurrence of one event precludes the occurrence of the other. Assuming that each person can have only one blood type, therefore having blood type O and having blood type A are two mutually exclusive events. The probability of having blood type O or A are the sum of probability of having blood type A and the probability of having blood type B. Looking at the previous table, we have 40 divided by 100 for the probability of O and 35 divided by 100 for the probability of A. The sum of these two probabilities are 0.75. On the other hand, if two events are non-mutually exclusive, which means they can occur at the same time, then to calculate the probability of A or B, we must subtract the intersection of A and B from the sum of probability of A and probability of B, because we don't want to count the intersection twice. Let's calculate the probability of being a male or having blood type O. First of all, you should determine if these two events are mutually exclusive. Can they occur at the same time? Yes. An individual can be a male and have blood type A. And meanwhile, there is an intersection between the two events. Then the probability of being a male or having blood type O is the probability of male plus the probability of blood type O minus the probability that A and B occurs at the same time. Before we talk about the multiplication rule, I want to point out that if you can calculate a probability using logic and counting, you do not need probability rule. When we calculate the probabilities involving one event and another event occurring, we multiply their probabilities. In some cases, the first event happen impact the probability of the second event. We call these dependent events. In other cases, the first event happen does not impact the probability of the second. We call this independent event. For the independent event, the probability of A given B is equal to the probability of B. We can use this formula to help you determine if two events are independent or not. When two events are independent, we can say that the probability of A and B is equal to the probability of A times the probability of B. Let's look at an example. We want to calculate the joint probability of being male and having blood type O. To know that two events are independent, we can compute the marginal and conditional probability of one of them. If they are equal, the two events are independent, and if they are not equal, the two events are dependent. The probability of having blood type O is 0.4. The probability of having blood type O among male is 0.4. We can conclude that these two events are independent. Therefore, the probability of being male and having blood type O is equal to the probability of having blood type O multiplied by the probability of being male. You have 40 divided by 100 times 50 divided by 100, which is equal to 0.2. Considering drawing two cards without replacement from a standard deck of 52 cards, that means we are drawing the first card, leaving it out, and then drawing the second card. What is the probability that both cards selected are black? We know that half of the 52 cards are black, so the probability that the first card is black is 26 over 52. But the probability of getting a black card changes on the next drawing. Since the number of black cards and the total number of cards have both been decreased by 1. Therefore, when two events are dependent, we need to multiply the multiplication rule. This new formula says we can multiply by the probability of two events, but we need to take the first event into account when considering the probability of second event. The vertical bar in the probability of B given A means given, so it could be read as the probability of B occurs given that A has occurred. In general, we can memorize the multiplication rule as the probability of A and B is equal to the probability of A multiplied by the probability of B given A. If the events are independent, one happening doesn't impact the probability of the other. And in that case, the probability of B given A is equal to the probability of B. Another example to illustrate how to apply multiplication rule to calculate joint probability. This table summarizes the number of ill and not ill for the outbreak of food poisoning. And we're interested to know the probability of being ill and consuming the barbecue. First, we can examine if the two events are dependent or not. The probability of being ill is 0.55, and the probability that an individual is ill given he or she has eaten the barbecue is 90 over 120, that is equal to 0.75. We can see two numbers are not the same, therefore we can conclude that these two events are dependent. Then the probability of eating the barbecue and being ill is equal to the probability of consuming the barbecue multiplied by the probability that an individual is ill given that she or he has eaten the barbecue. So we have 120 over 200 times 90 over 120, which is equal to 0.45. The Bayes theorem is named after Reverend Thomas Bayes, whose manuscript reflected his solution to the inverse probability problem. Computing the posterior conditional probability of an event, giving no prior probability related to the event, and relative conditions. The theorem came out of the understanding of that we cannot know the world perfectly, but rather can only hope to update our knowledge of it as increasing amount of evidence come to light. Probability of A is the probability of event A. Probability of B is the probability of event B. Probability of A given B is the probability of observing event A if B is true. The probability of B given A is the probability of observing event B if A is true. When probability of B is unknown, the formula can be written as one of the bottom of this slide. This alternative formula is derived from the first formula and is true when event A and event not A are mutually exclusive. Bayes' theorem is an example of subjective probability, and it is widely used when calculating screening test results. A patient goes to see a doctor. The doctor performs a test with 99% reliability. That is, 99% of the people who are sick test positive, and 99% of the healthy people test negative. The doctor knows that only 1% of the people in the country are sick. Now the question is, if the patient tests positive, what is the chance that the patient is sick? The solution to this question can be easily calculated using Bayes' theorem. The probability you test positive and sick is the probability of the likelihood that you test positive given that you're sick, and the prior probability that you're sick, which is the prevalence in the population. Bayes' theorems allow one to compute a conditional probability based on the available information. Based on the available information, we could piece this together using a hypothetical population of 100,000 people. Given the available information, this test will produce the result summarized in the table below. In this scenario, probability of A is unconditional probability of disease. Here it is, 100 divided by 10,000 is equal to 0.01. The probability of B is the unconditional probability of a positive test. Here it is, 198 divided by 10,000, which is equal to 0.0198. What we want to know is the probability of A given B. For example, the probability of disease A, given that the patient has a positive test B. We know that the prevalence of disease is 1% or 0.01. It is represented by the probability of A. Therefore, in the population of 10,000, there will be 100 diseased people and 9,900 non-diseased people. We also know the sensitivity of the test is 99%. That is, the probability of B given A is equal to 0.99. Therefore, among the 100 diseased people, 99 will test positive. We also know the specificity is also 99%. Therefore, among the 9,900 non-diseased people, 99 will have a positive test. And from these numbers, it follows that the unconditional probability of positive test is 198 divided by 10,000, which is equal to 0.0198. That is the probability of B. Thus, the probability of A given B is equal to 0.99 times 0.01 divided by 0.0198, which is equal to 0.5, which is 50%. Here's another example in which you can exercise Bayes' theorem. Let's say in Boston, 51% of the adult population are male. If an individual is randomly selected to participate in a study, then the prior probability of selecting a male is 0.51. We also know that 9.5% of males in Boston smokes as compared to 1.7% of females. I want you to find the probability that we select a male given he is a smoker. Please pause there to work on this question by yourself. Once you're done, you can compare your solution with mine. I find it helpful to list what probability I have before applying Bayes' theorem. I have the probability of male is equal to 0.51 and the probability of female equal to 0.49. Probability that an individual smokes given he is a male is equal to 0.095. And the probability that an individual smokes if she is a female is 0.017. I have everything I need to apply Bayes' theorem. Be sure to show your work on the exam to get partial credit if your calculation was not perfect. It is interesting that knowing the participants smoke increased the probability of selecting a male participant. I hope your answer is the same as mine. Please feel free to contact me if you have any questions.